Imagine a world where machines don't just follow instructions, but understand context, anticipate needs, and generate human-like responses in real time. That world isn't science fiction. It's the reality of modern large language models, and at the heart of their intelligence lies a single, deceptively simple mechanism: attention. But attention isn't just a buzzword. It's the architectural breakthrough that transformed AI from pattern-matching machines into reasoning systems capable of handling complex language, code, and even abstract thought. So how does it actually work? Let's dive deep, past the hype, past the metaphors, and explore the true mechanics of attention from the ground up. At the core of attention is a fundamental question: which parts of the input matter most right now? When you read the sentence, "The cat sat on the mat," your brain doesn't process every word equally. You're instantly drawn to cat and sat because they carry the most meaning. The and on are still important, but they're context providers, supporting actors, not leads. Attention does the same thing, but in math. It assigns a relevance score to every word in the input relative to every other word. This is called a query key-value mechanism, and it's the engine behind the entire system. Let's break it down. Each word in the input is first converted into a numerical vector, what we call an embedding. These embeddings capture semantic meaning, syntax, and position. Now for each word, we compute a query vector. Think of this as asking, what do I need to know about this word? The query is a way of probing the rest of the sentence for relevant information. Then every word also generates a key. The key is like a fingerprint, unique, descriptive, and used to match against the query. The system compares the query from cat to all the keys from the cat sat on the mat and computes a similarity score. The higher the score, the more relevant that word is to the current one. But raw similarity scores aren't ready to use. They're unnormalized and can be wildly different in scale. So we apply the softmax function. This turns the scores into a probability distribution. Now the sum of all relevance weights equals 1. The word sat might get a 0.45, mat a 0.25, the a 0.15, and so on. This is the attention distribution. Now comes the final step, the value vectors. Each word also has a value, what it actually contributes to the representation. The system multiplies each value by its corresponding attention weight and sums them up. The result? A single context-aware representation of cat that's been shaped by everything else in the sentence. This is the magic. The output isn't just about cat. It's about cat in context, how it relates to sat, mat, and even though. It's a dynamic, adaptive summary. But here's where things get even more powerful. Models don't use just one attention mechanism. They use multiple heads. In a typical transformer, you might have 16, 32, or even 128 attention heads, each learning to focus on different aspects of the input. One head might focus on subject-verb relationships. Another might track pronoun references. A third might detect syntactic structure. By combining all these perspectives, the model builds a richer, more nuanced understanding. This is why transformers outperform earlier models like RNNs and LSTMs. RNNs process sequences step by step, suffering from vanishing gradients and slow training. Transformers process all words simultaneously, parallelized, and use attention to capture long-range dependencies instantly. But attention isn't just about understanding. It's about generating. In autoregressive models, attention works in two layers. Encoder attention, which builds context for the input, and decoder attention, which uses that context to generate the next output word. As the model generates the cat, it asks, what should come next? It queries the encoder's representation of the full input, computes attention weights, and selects the most relevant features to guide its next prediction. And because attention is differentiable, it can be trained end-to-end using gradient descent. The model learns not just what to say, but how to focus, which parts of the input to pay attention to, and when. This leads to one of the most powerful features of attention: interpretability. We can visualize attention weights as heatmaps. In the sentence, she saw the man with the telescope. The model might focus heavily on telescope when generating with, revealing its understanding of the prepositional phrase. This isn't just a black box, it's a window into reasoning. But attention isn't perfect. It has limitations. The computational cost grows quadratically with sequence length. For a 10,000-word document, attention must compute 100 million pairwise interactions, something that quickly becomes prohibitive. That's why researchers are developing alternatives: sparse attention, sliding window attention, and methods like mixture of experts. But even with these innovations, attention remains the foundation. From the original 2017 Transformer paper to models like GPT, PaLM, and Llama, attention has enabled breakthroughs in translation, summarization, code generation, and more. It's not just a technique, it's the architecture that made modern AI possible. So the next time you ask a model to write a poem, debug code, or explain quantum mechanics, remember, beneath the surface, it's not just memorizing patterns. It's dynamically weighing every word, every idea, every connection, like a mind at work. Attention isn't just a component. It's the mind of the machine. The future of AI isn't just bigger models. It's smarter attention. And understanding it is the first step to shaping what comes next.